Our final piece of seafloor spreading data is number 3, magnetic reversal patterns. We've already seen a couple patterns spread across the entire ocean floor. We've seen the pattern of the age, starting out youngest right at the mid-ocean ridge, our major feature inside the ocean. We've seen the youngest start there, and the further we get away from the ridge, the older the crust becomes. We also have seen the pattern of sediment thickness. The further away we are from the mid-ocean ridge, the thicker that layer of sediment becomes. And both of those have to do with what's going on at the mid-ocean ridge. We know underneath the crust, the asthenosphere is pushing up magma to the surface, reaches the Earth's surface under the ocean, instantly cools, and becomes part of the oceanic crust, or the basalt. That's all happening at the mid-ocean ridge. We see a similar pattern here with our third piece of data, the magnetic reversal pattern. First of all, we want to know, well, what is a magnetic reversal? We already talked a little bit about one of the layers of the Earth, the outer core. The outer core, because of its consistency being liquid and made up of metal, iron, its materials and its movement, because it's liquid, creates a special feature on Earth called the magnetic field. So we know that Earth has that magnetic field because of its rotation, and the outer core being liquid rotates then inside of it. So that spinning or that rotation creates the magnetic field. The magnetic field is useful to Earth for a few different reasons. One, we found out about the magnetic field and were able to create a tool to give us direction based on the magnetic field, and that tool is the compass. And the Earth also is thankful for the magnetic field because it deflects particles from the sun. When the sun has a large flare, it sends particles towards our planet, and the magnetic field basically acts like a shield, keeping those solar flares off of the Earth. The magnetic field is not something we can see, but if we could, it would look something similar to this. Because of that rotation of the Earth's outer core, as it spins, we get essentially this force field of magnetics happening all around the Earth. So take a second, just look at this picture and draw in a magnetic field example on the right-hand side of your page. So what does this have to do with the ocean? Well, oceanic crust is made up of basalt. Okay, basalt, being an igneous or volcanic rock, means that it was formed from cooling of molten material. Magma, if we're talking about material inside the Earth, and lava, if we're talking about material outside of the Earth. So basalt is that igneous rock, meaning it started out as molten and over time has become cool. Well, volcanic rocks are oftentimes iron-rich rocks, and iron happens to be a material that is magnetic. There's not enough in basalt to have a magnet stick to it. However, there is enough in basalt for the tiny little minerals inside of it to align with the Earth's magnetic field. Because the minerals inside the rock are able to do this, what happens then is that material cools, it records or preserves which direction the Earth's magnetic field is at the time the rock was created. The magnetic field can either align north, which we call normal polarity, because that's what we're used to for the time frame that humans have been on Earth, or pointing towards the south, which we then call reverse. So minerals in lava initially are all mixed up every which way. They don't have a specific direction to them. So in the lava, minerals have no direction. They spin around as the lava moves inside the Earth or on the surface. So you can draw in a little picture on the right-hand side. When the rock is melted, there's no direction, or we can say no pattern. However, as the rock cools and becomes a solid, what we now notice then is that the crystals start to align. And again, they're aligning based on the direction of the magnetic field. So as the lava cools into basalt, those crystals go from having no pattern to all being aligned in one certain direction. So make sure you draw an example of what the minerals look like on the right there, both in lava when it's molten and solid when it's cooled into basalt. Like we mentioned previously, there are two types of polarity, because the Earth's magnetic field can actually switch or reverse over time. Normal polarity is recorded when objects have minerals that point towards the north. And again, that is currently what the Earth is now, so we've given it the name normal polarity. We see that the minerals inside the rock, this is like a basalt example, point towards the north. During times of reversed polarity, now the magnetized objects, or again, the basalt, have minerals that point in the reverse direction, which is of course then the south, the opposite of what we normally see. Humans have not actually witnessed or been around for a change in polarity, so not a whole lot is known about how it changes, but according to the rock record, it's pretty black and white. It's either normal, north, or reverse, south. As the rocks flip, there isn't much variation present. So let's see if we can indicate on each of the pictures on the right-hand side which Earth would be the normal Earth, where the magnetic field is pointing north, and which magnetic field would be the reverse for Earth, when the magnetic field is pointed south. Looking carefully at the arrows that are present, determine which field should be labeled as normal and which field should be labeled as reverse. So at this point you should be ready to plot your data. First thing we want to do is locate this section in our packet to make sure that we have the right data. And we're going to notice that we're recording two things in our rocks. We're recording the type of polarity and then the location. So we're looking at the distance here from Cape May, which is our New Jersey starting point. So the first one I want to record there is reverse. So I'm going to choose two colors. I've chosen blue and pink as my two colors to use. One to represent reverse and one to represent normal. So I have those two colors ready. I'm noticing here that the reverse is going to go from 0 to 350 miles from New Jersey. So I would like to take my reverse and color code all the way from 0 to 350 miles. This chunk of rock here, this part of the basalt on the ocean floor, is reverse. Reverse polarity. All the rocks are pointing to the south. Cross that one off. That is complete. My next is a normal, going from 350 to 630 miles. 350 to 630. All of that rock on the ocean floor is recorded as normal polarity, meaning all the minerals in the basalt are pointing to the north, all the magnetic minerals, the iron, and so on down the line. And I am going to do this all the way to the end, so I should get all the way to Portugal on the other side. Now some of your measurements might not be perfect. You might end up getting a reading that needs you to record at 800. So you might not be right on the line, but you can create your own as needed. So as we stated at the beginning, we had two pieces of evidence so far, age and sediment. Both showed a specific pattern on either side of the Midocean Ridge, and both showed a symmetrical pattern on either side of the ridge. And so we're seeing similar features for the magnetic reversals, right? Looking at your questions 16 through 18, we're going to organize our thoughts here on the pattern. So what we're seeing here is an alternating pattern of the type of magnetic reversals. We go from normal to reverse, normal to reverse, normal, and reverse. Like I said earlier, there's never an in-between as the magnetic field is switching around. It's always one or the other. When it is found in the magma or the lava, those minerals have no direct orientation. So we notice that the pattern is alternating as we go across the ocean, but looking around the mid-ocean ridge, we notice the pattern is both symmetrical and parallel. So here I go normal, reverse, normal, same thing on either side. When I have a thick layer, it's thick on the other side. When I have a thin layer, it's thin on the other side. So we're noticing a very symmetrical pattern right down to the inch. So let's label a few things on our picture there. In number 18, you want to make sure that your picture has magma similar to this one, coming up from the asthenosphere. So put a little magma bulb in there. Put an arrow, magma shown coming up out of the mid-ocean ridge. Label that as magma. We also want to make sure that we've labeled where the normal and reverse polarity can be found. Right? You've got an arrow pointing right at your main part of the mid-ocean ridge, making sure that that gets labeled as normal. That's the dark color, whereas the lighter color, that is the reverse. You can always remind yourself which way those minerals orient during those times of polarity. And the last one is we want to have arrows there showing how the crust is moving. We know at the mid-ocean ridge we have the youngest close and the oldest far away because the motion of the plates is going against each other. So each plate is moving away from the other plate. And this type of plate boundary is known as a divergent boundary. So again, how does all of this tie back to Alfred Wegener, right? What is the theory here of the seafloor spreading? Well, we notice that each pair of stripes on either side of the ridge is identical. They have similar composition, telling us they formed from the same place. They have similar age, telling us they formed at the same time, and the same magnetic polarity. The Earth had the same conditions. So each pair of stripes is discussing each set of reversals on either side of the mid-ocean ridge. So these two here are one pair. So because each have all those conditions the same, they must have formed at the exact same time from the same rock at the ridge, because that's in the middle. It's the middle proof of all of our evidence. We know this is possible because as the magma pushes up underneath the mid-ocean ridge, it slowly cools and creates new crust, slowly pushing that ridge apart. Right? As that magma comes up, oozes out to the surface. As it cools, it becomes hardened and slowly pushes the ocean apart. Now, because the continents are on either end of the ocean, over here South America and over here Africa are in turn getting further and further apart over time. As you finish up your notes and your diagrams on magnetic reversals, make sure that your graph has been totally completed. You've color-coded all the way across, and you've then answered the summary questions that occur on the back of the notes page.